Welcome to today's Explainer. We are jumping right into an absolutely wild roadmap today. We're going to trace how human understanding went from ancient stargazing monks who literally faced prosecution all the way to the applied physics that modern astronauts use to calculate orbital mechanics. Let's unpack the fascinating evolution of gravity. Here is our quick roadmap for today. We'll start with ancient myths and the heliocentric truth, move through Kepler's and Newton's laws, see exactly how Cavendish weighed the Earth, and finally we'll crunch the numbers on escape speed and orbital energy.
Section 1. Ancient Myths to Heliocentric Truth.
Putting on my historian hat for a second, let's look at how early humans first made sense of the stars. It's an incredible timeline. 2,000 years ago, you have Ptolemy proposing the geocentric model, Earth at the center. By the 5th century, the Indian astronomer Aryabhata mentions a heliocentric model, which Copernicus then definitively locks in during the 16th century. After that, Tycho Brahe records this unbelievable naked-eye data, Galileo proves uniform acceleration, and finally, Johannes Kepler extracts his famous laws.
Now, what is truly fascinating here is the massive historical struggle this represents. Think about the conflict between early scientific models and traditional church beliefs. Supporters of the heliocentric truth, like Galileo, actually faced state prosecutions simply for challenging the idea that Earth was the center of everything. It wasn't just a debate, it was a major turning point in scientific discovery.
Section 2. Kepler's Laws of Planetary Motion. So Johannes Kepler takes his mentor Tycho Brahe's lifetime of naked-eye data and he completely changes the shape of our universe. He shifted astronomy away from perfect circles to elliptical paths. It's actually super easy to visualize. If you fix 2 pins into a board, with one representing the sun, loop a string around them, and draw with a taut pencil, you get an ellipse. It's a simple analogy, but it beautifully broke the Copernican mold forever.
And that brings us to his second law, the law of areas. The absolutely crucial takeaway here is that planets travel faster when they whip near the sun at the perihelion, and they move slower when they're farther away at the aphelion. Why? Because of the conservation of angular momentum. The planet physically has to speed up to sweep out the exact same area in the same amount of time. If you want proof of Kepler's law of periods, just look at the raw observational data. The square of a planet's time period is always proportional to the cube of its semi-major axis. Whether it's Mercury or Jupiter, that quotient is consistently right around 3.00. It's just this elegant mathematical harmony hidden right there in the heavens.
Section 3. Newton's Universal Gravitation Law. We all know the legend of the falling apple, right? Well, Isaac Newton used Kepler's laws to establish something truly universal. In plain, everyday language, his math simply means that gravitational force weakens dramatically as the distance between objects increases. If you double the distance between 2 masses, the force drops by a factor of 4, because it's inversely proportional to the distance squared. So how do we actually calculate this force? Here is a super practical step-by-step tutorial. First, you multiply your 2-point masses together. Then, you multiply that by the gravitational constant, big G. Finally, divide all of that by the distance between them squared. It is literally the exact same math that pulls an apple to the ground and holds the moon in its orbit. Section 4. Cavendish weighs the Earth. But here's the catch. To make Newton's math actually work in the real world, we needed the exact value of that gravitational constant G. Enter the brilliant Henry Cavendish in 1798. By using a simple twisting wire to measure the microscopic attraction between lead spheres, he found G. With that one missing puzzle piece, physicists could finally physically weigh the entire Earth.
Okay, transitioning into astronaut mode here, let's test your physics intuition before we leave Earth entirely. Quiz time. What happens to gravity when you dig down? Take a second to think about this. If you are getting closer to the center of the Earth, does the gravitational pull get stronger or weaker?
Surprisingly, it actually decreases. The outer shells of the Earth perfectly cancel each other out, leaving only the mass of the smaller sphere beneath you pulling you down. But a quick caveat here. While the math neatly cancels out the forces of that outer shell, actual gravitational shielding using spheres is physically impossible. You can never truly block gravity. The forces just cancel each other out.
Section 5. Escape speed and gravity.
Let's dive into the mechanics of actually launching an object into space so it never, ever falls back down. By using the principle of conservation of energy, we can calculate this escape speed. We set the total mechanical energy required to reach infinity to 0.
which lets us solve the equation for the exact initial velocity you need at the Earth's surface.
And the final number is absolutely dramatic. To escape Earth's gravitational pull, you need to travel 11.2 kilometers every single second. If you hit that speed, your kinetic energy perfectly overcomes the negative gravitational potential energy tethering you to the planet.
Now, this concept directly explains why the moon is entirely missing an atmosphere. Because the moon's escape speed is a mere 2.3 kilometers per second, gas molecules easily heat up, hit that speed limit, and just escape forever into the vacuum of space.
Section 6. Orbital Energy and Satellites.
Now that we are officially in orbit, let's talk about the delicate orbital physics keeping our satellites in motion. For a satellite to stay in a bound system, its total mechanical energy must be negative. We defined gravitational potential energy as negative because you physically have to put work into the system to pull a mass away to infinity. Kinetic and potential energy are constantly trading off as a planet moves in an ellipse, but if that total energy ever hits zero, boom, the object escapes.
Here's something that feels a bit counterintuitive. When you transfer a satellite from a lower circular orbit to a higher circular orbit, you increase the potential energy, but you actually reduce the kinetic energy. You fire your rockets to get higher, increasing your total energy, but once you finally settle into that larger orbit, your actual traveling speed is slower than it was down below.
To wrap up our astronaut briefing today, here's a quick summary review. Escape speed relies strictly on planetary mass and radius. Total orbital energy is always negative. And remember, astronauts floating in the space station aren't actually in zero gravity. They are just in continuous freefall towards the Earth at the exact same rate the Earth's surface curves away from them.
I'm going to leave you with one final provocative thought to ponder. If the Sun is so unbelievably massive and its overall gravitational pull on the Earth vastly dwarfs that of the Moon, why does the tiny Moon rule our ocean tides? It is a fascinating puzzle that perfectly tests everything we've just learned about the inverse square law of distances. Thanks for joining me on this explainer today, and keep looking up.